Hello, you're tuned into a screencast on how to write formulas for a first-year chemistry class. Now, we're taking a look at formula writing and how it applies to ions, and it makes sense kind of to start this conversation or this discussion, or if you rather, this lecture, with taking a look at what ions are and how they're made. So what exactly are ions? Well, we really have two types of ions, which are atoms with charges, and they can be either cations, which are positive, meaning that the number of protons is greater than the number of electrons, or we can have anions, which are negative, which means the electrons outnumber the protons. Now, keep in mind from when we talked about atomic structure that you actually change the number of electrons in order to establish a charge. So the protons are determined by the atom present, the element present, and then from there we can change the electrons to get there. So how exactly are ions made, or how are ions formed? If we take, for example, a neutral atom of sodium, and we were to take a look at the electron configuration for sodium, most of you at this point would write something like this: 1s2, 2s2, 2p6, 3s1. And that last bit of information that's written, the 3s1, at the end of the electron configuration, that means that sodium, the element sodium in its neutral state, contains one valence electron. So in terms of structure, that means if you look at a sodium atom, and using Bohr's model of the atom, we take a look at the concentric rings of energy level that are written around this. The first energy level has something like 2 electrons. Now, even though this is not quite an appropriate model for the true structure of the atom, it works for this purpose, so bear with me here. So we've got 2 electrons on the first energy level, and then we've got 8, 3, 4, 5, 6, 7, 8, and then way out here all by itself is that valence electron. Now, you may notice all of these electrons in the middle here act as a shield, separating our little tiny nucleus in the middle from this outermost electron. That means that since there's one electron all by itself way out there, it's real easy to remove. And we call this in chemistry ionization energy. We would say that sodium has very low first ionization energy compared to something else in the period, on the periodic table, for example, the element chlorine. And if you take a look at the element chlorine, the electron configuration looks something like this: 1s2, 2s2, 2p6, 3s2, 3p5. Since there's 5 electrons in the outermost energy level, the outermost orbital of the highest energy level, a total of 7 valence electrons here on chlorine, it's going to be very difficult, if you sketch out Bohr's model of chlorine, to remove all 7 of those electrons. But what we can do is we can add 1 electron to it in order to complete that third energy level. So what actually happens here when you take 2 atoms, one with low ionization energy and one with high ionization energy, or, if you rather, one with low electronegativity like sodium and one with high electronegativity like chlorine, and you combine them chemically through a process, there's a transfer of electrons. So this one valence electron from our sodium actually gets transferred to here. When that happens, this energy level becomes empty on the sodium atom, and we end up with sodium with a positive 1 charge, since we lost that valence electron and now the protons outnumber the electrons. Well, what happens is that outermost electron, that valence electron from sodium, is taken into the last energy level on the chlorine atom, and it goes to 3p6. And in that process, the chlorine atom takes on a negative 1 charge and becomes an anion. So it's all about that ionization energy, electronegativity, and the attractive forces between the nucleus and the electrons that make this all happen. I'm not sure if you find this as exciting as I do, but the fact that one electron being transferred can totally change how an element acts is pretty impressive. And so if we look at the formula of monatomic ions, this is one of those things that you need to be able to do in chemistry. And if it's monatomic, that word right there means one atom. We use the periodic table to help us predict the charge. So if we were to sketch a periodic table here, we're going to do two things right off the bat here. We're going to, for this introductory topic, we're going to not look at the transition metals at all. And as a matter of fact, we're not going to talk about the noble gases at all either. So way over here on the far left is column 1A, or the alkali metals. The most common charge of any element in the first column of the periodic table will be a positive 1 if it's involved in an ionic compound. Column 2A, the alkali earth metals, most commonly are a plus 2. If you're a metal found in column 3A, that starts with boron, we're going to just make the assumption for our first year chemistry class that the most likely charge you're going to have is a plus 3. Column 4A, I'm going to skip for right now. So that leaves us with 5, 6, and 7A. Those columns right here. So our charge goes from positive 1 to positive 2 to positive 3. And then when we get into the nonmetals in column 5, we're looking at negative 3, negative 2, and negative 1 as we go columns 5, 6, and 7. So that allows us to use the periodic table to predict it. There's two other elements that we work with quite a bit in first year chemistry, which are monatomic, and it's zinc has a positive 2 charge, and silver has a positive 1 charge. So somehow, some way in your notes, you've got to remember how to do this for the formulas of the monatomic ions. What does all this mean? As an example, the element lithium is in column 1A. If we were to look at the most likely charge of an ion containing lithium, since it's in column 1A, it would be a plus 1 charge. If we take a look at an element like chlorine, which is in element 7A, the most likely charge of a compound containing an ion of chlorine is negative 1. Things like nitrogen in column 5A, most likely charge would be a minus 3. And it's all about finding these elements on the periodic table. Magnesium is an element 2A, metal. So we got magnesium most likely is going to be a plus 2 charge. What about the polyatomic ions? There's a whole bunch of polyatomic ions that are included in a packet of information, and I encourage you to use that packet of information to learn all you can about the formulas and the names of these polyatomic ions. Most of them end with the suffix of ATE, and they combine an element with oxygen for those. Now, if you're looking at the polyatomic ions, there's only one cation on that list. And this one, you just kind of have to commit to memory. Its formula is NH4 with a positive charge, and its name is ammonium. So you can see what I mean by a polyatomic ion here. It's more than one atom. It's nitrogen and 4 hydrogens combined together, and they have a charge of plus 1. So it's more than one atom with a charge. That's a polyatomic ion. Some of the other ones that you definitely need to know are things like acetate, C2H3O2 negative is acetate. You also need to know, for example, sulfate, SO4 negative 2. Nitrate shows up very commonly in our discussions in first year chemistry, NO3 minus 1. Carbonate, which is CO3 minus 2. Phosphate is PO4 minus 1. Hydroxide is OH minus 1. I'm sorry, on the phosphate, it should be PO4 minus 3. I got a little carried away there, over anticipating hydroxide coming next as a negative 1. So there are about 7 polyatomic ions you definitely need to know. If you highlight those on your list or whatever, these are the ones we see most often. Now, in class, your teacher might show you a method for using the periodic table to determine how many oxygens go with each element. And we can discuss that later if you need help. So how do we put the ions together to make formulas? When we start off this conversation, we actually give you, as a student, the formula of a cation and the formula of an anion. So we're going to take a look in this first case scenario at calcium with a +2 charge, and we're going to compare it to sulfate with a -2 charge. I'm also going to do sodium, +1, and we'll also take a look at chloride, -1, so we can kind of see how this works. And then the last one I'm going to show you involves the cation ammonium +1 and phosphate, which is PO4 -3. So the important thing here when doing this is the charges. When all is done, the charges have to add up to be 0. So what we do is we always write the cation first. So if we're combining calcium and sulfate, I'd move the symbol calcium over into our problem here, and I'd bring down the sulfate, SO4 -2. The next thing we want to do is we want to actually check the charges. Calcium has a charge of +2, and sulfate's a -2. +2 and -2, those add up to be 0. What happens, though, when we take, for example, the sodium cation and put it with the sulfate anion? So the sodium is a +1 charge, and the sulfate's a -2. That doesn't add up to be 0. So we need to find a common multiple would be the language that we frequently use of 1 and 2, and the common multiple of 1 and 2 is 2. So we have enough sulfates. We have a -2 charge from that, but we have a +1 for the sodium, so I need another sodium. So we put a subscript 2 on the sodium to show that. So now I have 2 sodiums, each with a +1, and a sulfate that's a -2, and those charges cancel out. They balance when we write that formula. All right, so let's use what we know then and take a look at the calcium cation with the chloride anion. Calcium is a +2 cation, and chloride is a -1 anion. So that means in order to get this to balance, we need 2 chlorides. That makes sure that these 2 charges cancel, and our formula unit is electrically neutral. Sodium and chlorine, chloride ion, when we take a look at those, we've got a +1 and a -1. Those 2 add up to be 0, and our formula unit is electrically neutral. What I'd encourage you to do is I'd encourage you, if you're trying these problems, to pause this screencast right now and try the ammonium and phosphate column and row and see what you end up with. And we'll see you back in just a few seconds. Well, hopefully you just hit pause and you're back and you're taking a look at this screen and hoping to see how this all works out. So I'm going to write in green, just so you can see this, the correct formula for the combination of NH4 and sulfate together involves 2 NH4s and 1 sulfate. The formula for NH4 and Cl is NH4Cl, +1 and -1. And then the last formula, NH4, but we need 3 of them for every 1 phosphate. What about the rest of the phosphate column? We'd have 3 sodiums, because they're a +1, to every 1 phosphate. And then finally, the common multiple of 3 and 2 is 6, so I would need 3 calciums, each one's a +2,